Hi, welcome to our next level 3 differentiation video. In this video, we're going to explore the second derivative. A stationary point is a point on a function where the gradient is 0. Stationary points can either be maximum or minimum turning points, but also can be points of inflection because some points of inflection have 0 gradients. We can use the second derivative to determine the concavity of a function. Hence, we can identify if it's a maximum or a minimum turning point, and we can also use the second derivative to help us locate the points of inflection. Right, here's some notes that may be worth stopping and copying these down to remember them. If the second derivative y double dash is less than 0, we say the function's concave from below. If the second derivative y double dash is greater than 0, we say that the function is concave from above. And if the second derivative is actually 0, we say it's most likely a point of inflection, though it's not always. Right, let's get into example 1. We're going to determine the nature of the turning points and also the location of the point of inflection for the function y is equal to x cubed minus 3x squared. Right, so step 1 is we work out the gradient rule by differentiating. We're going to put the gradient rule equal to 0 to find the turning points. And that tells us that we have 2 turning points because it's a quadratic, and the first is 0 and the second is 2. Right, now we're going to work out the second derivative, which is y double dash. We're going to take our two x values and substitute them into the second derivative. So when x is 0, we get a value of negative 6, and when x is 2, we get a value of positive 6. Right, going back and looking at our notes from before, we can see that when the second derivative is less than 0, we are concave from below. And when the second derivative is greater than 0, we're concave from above. So looking at what the function looks like, when x is 0, we are concave from below, and it is a maximum turning point. And when x is 2, we are concave from above, which gives us a minimum turning point. Right, now we're going to go on. We're going to take the second derivative and put that equal to 0. And we're going to solve it to get x is equal to 1. We're going to take that value of 1 and substitute it back into the y function, not y dash or y double dash. And we're going to get a value of negative 2 for y. So we have this point 1, negative 2. And when we draw the function once more, hopefully you can see that those are the one point is the point of inflection at 1, negative 2. Right, cool. Let's move on to example 2. We're going to determine the nature of the turning point and also the location of the point of inflection for the following function. Y is equal to x plus 3 all to the power of 4. So the first thing is we're going to differentiate it to get the gradient rule. The 4 comes out the front. We leave x minus 3 alone. We drop the power of 4 to a 3. And we times by the inside function differentiated, which is 1. Now we're going to put the gradient rule equal to 0 to find a stationary point. Right, we'll solve that. The only solution is 3. So when we draw a picture of the graph, we can know that there's a stationary point when x is 3. When we create the second derivative, the 3 comes out the front to get 12. We leave the x minus 3 alone, drop it to a power of 2, times by the inside function, which is 1. We get 12 times x minus 3 all squared for our second derivative. Now we're going to take the value of 3 and substitute it into the second derivative, and we're going to get 0. Now normally that suggests it's a point of inflection, but we're going to test it because it might not be. So let's check it when on one side of 3 at 2, substitute that into the gradient to get a negative gradient. And let's substitute that into the other side of the gradient of 3 and get a positive gradient. And you can see that it is not a point of inflection. It is indeed a minimum turning point. Great. Thanks for watching.